Hello everyone. Today we are going to discuss the problem coin collector from CSES Graph problem set. Let's go through the problem. A game has n rooms and m tunnels between them. Each room has a certain number of coins. What is the maximum number of coins you can collect while moving through the tunnels when you can freely choose your starting and the ending room? So the first input line has two integers n and m, the number of rooms and tunnels. The rooms are numbered 1 to n. Then there are n integers k1, k2 up till kn, the number of coins in each room. Finally, there are m lines describing the tunnels. So each line has two integers a and b, which says that there is a tunnel from room A to room B, and each tunnel is a one-way tunnel. So you have to print the maximum number of coins you can collect. Okay, cool. So the number of rooms are of the order of 10 power 5. Number of tunnels again are of the order of 10 power 5, and number of coins in a room can go up till 10 power 9. So let's first of all try to understand what the problem is, and then we will see how we can actually solve this problem. So I have just copied this input example over here. So we have rooms 1, 2, 3, 4. We have tunnel from room 1 to 2. As you can see, 1 to 2, then from 2 to 1, then from 1 to 3, and then from 2 to 4. And room 1 has 4 coins. 2 has 5, 3 has 2, and room 4 has 7 coins respectively. Okay, so this is the input given to you. Now let's try to understand what we actually need to do. We can choose any starting room. We can choose any starting room, and we can choose any ending room. And we have to collect maximum number of coins. Okay, let's suppose I tell you that I am choosing room 1 as a starting room. Okay, so let's see how we can collect a maximum number of coins. Let's suppose from room 1 I decide to go to room 3. If I decide this particular path, then from 3 I don't have any more path, right? So the number of coins I was actually able to collect was the coins from room 1 plus the coins from room 3, that was 4 plus 2, that is 6, right? Let's suppose I started from room 1, then I went to room 2, and then I started from 1, I went to room 2, and then I went to room 4. Now from 4 I don't have any other path, so the total number of coins I have actually collected is 4 plus 5 plus 7, which results into 16. So 4 plus 5 plus 7, that results into 16, right? Cool. So if you just notice, I could have done like this as well. I would have started from room 2, then I would have went to room 1, and then I would have again returned to room 2 and then went to room 4. This also results me in the same number of coins, that is 16. Also, I have this particular path where I am starting from room 2, going to room 1, and then going to room 3. So in this, the total number of coins I will collect is 5 plus 4 plus 2, that is 11. So you can see that among all the paths that I have, among all the possible different combination of starting and ending points that I have, the maximum number of coins I am able to collect is 16. So the answer to this particular input example will be 16. Right? So I hope the problem is understood to each and every one of you. So now how we can actually solve this? So before moving ahead with the solution, I would just inform you guys that a prerequisite for solving this problem is going to be SCC, that is strongly connected components. So I have already discussed this particular concept in one of the videos. So in detail, it is a bit longer, but yeah, I have discussed each and everything in that particular video. So you can watch that first and then come back and watch the solution for this particular problem. If you know SCC from before, you are good to go to watch forward. Okay, cool. So how we can actually solve this? Now, when I see this question, and it is said that you can start from any, you can choose any starting point and you can choose any ending point. It says like this, right? So one thing that comes to my mind is DP. That is, I have multiple options and I have to take maximum from all the multiple options, right? And I also know that I have read about a concept of DP in acyclic directed graphs. This concept is very famous, right? DAG, DP in DAGs. We also say DP in DAG, that is directed acyclic graph. So we know that this concept exists, but the graph given to us can be cyclic, right? As you can see over here only, that this is the cycle that we have. If you just notice, this is the cycle that we have, right? You can already see a cycle over here from 1 to 2 and from 2 to 1. So what we should do so that this graph gets converted to directed acyclic graph. Do we have any mechanism via which we can convert this graph to a directed acyclic graph? Do we have any mechanism? The answer is yes. The answer is yes. And how we can do that? We can convert that particular graph to a directed acyclic graph by condensing that graph. So when we have strongly connected components, what we do is we take all the nodes of a single strongly connected component as a one big node, and we construct a graph with those big reconstruct the graph with those big nodes. So the graph that will result after that is actually a directed acyclic graph, which is also known as condensed graph. Let me take an example. You guys will understand it better. So if let's suppose I have this particular graph with me. Let's suppose this is the graph that I have. Okay. And these are the edges. Let's suppose these are the edges that I have. Okay, and let me number the nodes as well. So node 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In this particular graph, okay, sorry, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. In this particular graph, can you guys figure out the strongly connected components? Can you guys do that? This is one strongly connected component that I can see. Okay. This is one strongly connected component that I can see. Cool. This is the another strongly connected component that I can see. This is the other strongly connected component. And this is the other strongly connected component. Right? So this graph consists of 4 strongly connected components. Now, if you guys know strongly connected components, so I hope you guys know that how do you actually get the components? You get the components in this form, right? Vector of vector int components. you can get components in this form, right? So let's suppose I have the vector of components. So this will have elements something like this. So the first will have 1, 2, 3, and 4. Then I will have 5 and 6. Then I will have 8, 9, 10. Let me draw one more edge over here. Okay. Then we will have 8, 9, 10. And then we will have 7. This is what you will get as a result of SCC. Like when you separate out strongly connected components, this is what you will get as a result. And if you just consider these as nodes, if you consider this as node 0, this as node 1, this as node 2, and this as node 3, the graph that you will get is, this is SCC1, this is SCC1, this is SCC2, this is SCC3, let's suppose, and this is 4. So basically this is node 0, node 1, node 2, and node 3. And now if you draw the edges, so you can see that from this SCC1 you had the edge to SCC2 and SCC3. So basically from 0 you have an edge to 1, and from 0 you have an edge to 2, right? Now again from SCC1, from SCC2 you have then edge to SCC3 and SCC4, and to SCC4 you have actually 2 edges, right? So if I draw this, it will look something like this. From node 1 you have a node 2, node 2. So you have an edge something like this, and you have an edge something like this. From 2 you have to 3, and then from 1 you have actually 2 edges to 3. So this is how the condensed graph will look. This is how the condensed graph will look like. And just say me one thing, can this condensed graph be cyclic? Can this condensed graph be cyclic? Just tell me one thing. It can't be cyclic, right? This condensed graph can't be cyclic, because if it was a cycle, let's suppose 0, 1 and 2 together would have formed a cycle, then the 0, 1 and 2 would have been part of the same strongly connected component. But we know that 0, 1 and 2 does not form the part of same strongly connected component. They are separate strongly connected components. Hence, we can say that this graph will always be acyclic. And now since it will be acyclic, we can apply DP over here, right? How will we apply DP? So for node 0, we can find the total sum, total coins. How we will do it? We know that for 1, how many coins was there, for 2, 3, 4, we know the number of coins, right? So for component 0, we can find the total number of coins. Again for 1 we can find, for 2 we can find, for 3 we can find. And we can apply simple DP over here. How will we do that? How will we apply DP over here? It's pretty simple, right? What we will do is, okay. So let's suppose take over here only. We will have, let's suppose some answer vector. Okay. So when we traverse from some particular node, let's suppose I am starting my DFS from this particular node 0. Okay. So if I do that, so let's suppose this 0 has C1 coins, this has C2, this has C3, and this has C4. Okay. So I have started my DFS from, let's suppose, 0. So for 0, I have two possible paths, right? I can either go to this node 1 or I can either go to this node 2. So I will try to get the maximum sum. I will try to get the maximum sum for this 1 and 2. So let's suppose I first of all start from here. From 0, let's suppose first of all went to 2. So if I go to 2, So what is the maximum number of coins for 2? So for that I will explore for 2. So from 2 I go to 3, and from 3 there are no other options, right? So for 3 I can write that if I start from 3, the maximum number of coins that I will get is actually C4. I am pretty sure of this. So in answer of 3, I will have C4. Now from 3, I will return back to 2. And for 2, there are no other possible options, right? So can I say the maximum number of coins I will collect if I start from 2 is C3 plus C4? Can I say this? Right. So I can write answer of 2 as C3 plus C4. And now I will again backtrack. From 2 I will go to 0. Now from 0 I know that if I am choosing this particular path, so the maximum number of coins that I will be able to get is actually the maximum number of coins 2 has plus C1. So if I am choosing this particular path, the maximum number of coins I will be able to get is C1 plus C3 plus C4. But I have one more possible option. So from 0 now I will traverse this particular path, 1. So from 1, again I will try to see maximum number of coins I will get if I start from 1. So again there are two options. I either go to 2 or I go to 3. If I go to 2, I already have the answer computed for 2. So I won't again do my DFS from 2. I have that if I start from 2, the maximum number of coins I will get is C3 plus C4. So this 2 will actually return C3 plus C4 to this node 1. So I am sure that if I start from 1, the maximum number of coins I will be able to get is C3 plus C4 plus C2. Now again, if I start from 1, there is one more option as well, that I go to this node 3. So again for node 3 the answer is already computed, that is C4. So I will simply return C4. So from 1 I know that if I choose this particular path going to node 3, I will end up having the number of coins as C2 plus C4. So maximum of these two is this particular thing, C3 plus C4 plus C2. So for answer of 1, we will write answer of 1 will be C3 plus C4 plus C2. So for this node 0, I know the maximum sum that I can get if I choose this particular edge or this particular path is nothing but C1, that is from this particular node, plus C3 plus C4 plus C2. So now again for this node 0, I have two paths and the maximum, as I can see over here, is this particular value. So I will write answer of 0 as C1 plus C3 plus C4 plus C2. This is how, just by simple DP computation, I can find the maximum sum for each and every node. That is, if I am starting from that node, I can find the maximum sum that I will achieve, maximum number of coins basically that I will achieve if I start from that particular node. So this is how you can actually solve this problem. So also you know that since these components are always, the components that we will get will always be sorted in topologically sorted order, right? We are very much sure of this. So the concept, when we discuss strongly connected components, we have discussed that over here, that what is the reason. I hope if you already know SCC, you know that this will always be sorted in topologically sorted order, right? Cool. So now let's see the code for this for better understanding. So here is the code for strongly connected components. So this helper function will actually give me vector of vector int. So basically it will give me list of all the strongly connected components. Okay, to this I am passing the number of nodes and the edges. Okay, so let me just quickly go through this particular code first. So over here I am constructing the graph, and the graph with reversed edges, doing a topo sort because we will traverse in the reversed edge graph in this particular order for getting the SCC, and then traversing in that order and getting the strongly connected components and returning it. So you can see this code. I will just attach the link in description. But this is something that I have already discussed in my video of strongly connected components. So you can definitely go through that video if you want to understand this particular code. This is not a very tough concept. It is very, very easy if you understand it, that why we are doing the things. So it's not tough. Okay. Now let's see how we will use this strongly connected components to solve this particular problem. So I am taking the two nodes n and m, two input lines n and m. Basically n is the number of nodes, m is the number of edges. Then taking the coins input for each and every node, and then taking the input of edges. So you have u and v converting to zero based indexing, and in my edges I am pushing back u and v. So now from this helper function I will get these components. The number of components I am assigning to variable k. Now I have three things. First is the component sum. So for every component contains multiple nodes, right? So for every component, I will compute the component sum. Then I have some variable num as 0. This is basically the component number. And I have vector in component number n. So this will tell me basically that for every node, what is the component number, okay? So I go over every component in components, initialize my request value to 0. This is basically for finding the sum, total sum for the component. So going over every node in the component and updating my request value, adding coins of node to it. And component number for this particular node is going to be num. So once I am done for a particular component, I am increasing the component number. And in my component sum, I am pushing back this request value. So basically, component sum will contains the sum of all the coins for a particular component, and component number will contain that for every node, what is the component it belongs to. Why I am using this component number? Because this will help me to construct the this condensed graph, this SCC graph basically. So how I am constructing the SCC graph? So first of all, making this adjacency list, the size will be k, right? Because the number of nodes in this SCC graph is going to be the total number of components, that is basically k. Now going over all the edges, the first node is stored in the first value, second node is stored in the second value. I have taken input of the edges as pair, right? Okay. Now if the component number of u and v are not same, that is, it does not belong to the same SCC. So in that case, in my SCC graph, for component number u, whatever is the component number of u, in that I am pushing back the component number of v. So we are actually pushing the component number in the SCC graph. Like once we do that, so this is how my SCC graph will look like. This is how my SCC graph will look like. This is the SCC graph or the condensed graph that we have actually formed. Now once we have done, now the things are very easy. Initializing my answer vector to size k, initializing my maxi variable to 0. Just ignore this for now. Going over every node in the condensed graph and doing a DFS from there. So I have just written a lambda function over here. And once the DFS is done, I am updating my maximum variable to max of whatever the maximum variable is, comma, answer of I. Why I am doing like this? Because there can be some disconnected components as well. Like this is one component that is forming. It may be that the components are not connected only. Like I can have some more nodes 5 linked to 6 like this. There can be some disconnected components as well. So for that reason, we have to do like this. Okay. Now if the answer let's see what we are doing in the DFS function. We are taking the node as input. This is a recursive lambda function. So this is how we actually write it. If answer of node is not 0, then I am simply returning. This means that for that particular node, the things are already computed. So I don't need to recompute that. So this is where actually we are using the DP concept. So now if the answer of node, in my answer of node, I am adding the component sum for that particular node, initializing my maxi variable to 0 and exploring all the options from that particular node. So for every node that has an edge from this particular node, I am just doing a DFS and updating my maxi variable, this maxi variable to max of maxi comma, whatever is the answer of IT. Once I am done with this, so I know that for every node, there can be multiple options, right? I only need to take the maximum of all. So I took maximum of all, and in my answer of node, I just added that value. Because the answer of node will be the component sum for that node plus the maximum of all the options that I have. Once I am done with this, I am just updating my maxi variable, so just don't get confused by this maxi variable and this maxi variable. I mistakenly took these variables name same, but okay. This maxi variable is for this DFS function. This maxi variable is the overall maximum that we are computing. Okay. So this is how you can actually solve this problem. So this was actually a very beautiful problem where we are actually using the concept of strongly connected components to convert the graph to DAG, that is directed acyclic graph. For SCC, we also say it as condensed graph, and then using DP over there. So we have already done problems of DP in DAG. We have already done problems of strongly connected components. It was basically the combination of both of them. So I hope all of you understood it. Thank you.